Hello, hello, hello. This dynamics lab number 6 dynamics. Um, Let me make sure that I'm sharing my audio. I am also sharing my video. Okay. And right now I'm also sharing the application window, and I'm going to use a whiteboard. All right. So this is lab 6. So lab 6 is about dynamics. Dynamics. Well, what's dynamics? Well, dynamics has to do with why objects move. And when we talk about why, we look at the forces involved. And the most important law in dynamics is the second law, where we look at why objects accelerate. So second law says that uh, Newton's second law, it says that the net force is equal to mass times acceleration. Net force acting on the object is equal to mass times acceleration. And as we try to study this one, then we are in the realm of dynamics. The other areas like kinematics, we try to describe motion. We use terms like speed, velocity, acceleration, etc. But when you go to dynamics, we look at the forces. Okay. So F net equal to mass times acceleration. What does this mean? So there are two important ideas here. Let me also put, like, if these are vectors, then I can do, like, they are vectors actually. Acceleration and force. There are three meanings from the formula. Number one is that acceleration is directly proportional to the net force. So I can get meaning out of the formula, saying that acceleration is directly proportional to the net force. And two, I can say that acceleration is inversely proportional to the mass. Acceleration is inversely proportional to the mass. Proportional to the mass. So what does this mean? It means the more the mass, the less the acceleration, and vice versa. And the first one says that the more the net force, then the more the acceleration. All right. So these are just coming out of the equation itself. Number three, we can say that acceleration is in the same direction, as the net force. Okay, because the force and acceleration are vectors, and for this equation to be meaningful, then the net force and acceleration must be pointing in the same direction. Our job today is to actually verify this equation. Specifically, we are going to verify that acceleration is indeed proportional to the net force. Okay, so here is our experimental setup. experimental setup. Okay, to do this experiment, we need to find a way to change the net force and observe the acceleration. So we need to find to design an experiment whereby we can vary the net force and observe the resulting acceleration. So the experiment we have a table like that, and we have a pulley here, and we have a mass here, and then we have a string or a rope that goes through the pulley and is connected to the hanger that has some mass here, small here, and we have a bigger mass on top here. All right, so that's the setup. What we'll be doing is to add mass here and observe acceleration. So we are going to actually get some mass from this larger mass and put it here, and then take our measurements. And then take some mass from M and put it here, get our measurements. The idea is we want to keep the total mass M, small m, and capital M the same. That's the idea. So we want to keep the total mass the same and then observe the relationship between net force and acceleration. Now let's look at the dynamics here, the way things are here. First of all, please take note that this one is frictionless. Frictionless. So frictionless surface. We are going to use actually air track. So it's actually air track. So air track is used for this experiment to provide a frictionless surface. This mass here is the one that is pulling the system, or is the one that is giving us the gravitational force. So there is gravitational force downward here, Fg, and Fg, remember, is given by small mass m times little g, which is 9.8. Okay, so that small mass, the small mass Fg is actually accelerating the little mass. So Fg is equal to mg. At the same time, we see that Fg, if we look at Newton's second law, let me just remind you that second law says that net force is mass times acceleration, and therefore if a net force is Fg, I have to look at all the mass that is being accelerated. So right now Fg is pulling down two masses, the small mass and the bigger mass. So our aim in general goes to that, and then times acceleration A. So there are two ways to understand the gravitational pull downward. So one, gravitational pull downward is just given by little m times g. That's the gravitational force acting on the that's force of gravity, the force of gravity due to the small mass. But at the same time, we can write Fg as the total system mass. We're going to call this one system mass, the total mass times the acceleration of the system. So there are two ways to understand Fg. We can understand it this way, and also we can understand it this way. This means we need to find an experiment whereby we will be changing the gravitational pull and then observing the acceleration. hopefully, the more the Fg, which is our net force, the more the acceleration. But we should keep this one constant. So our idea, experiment-wise, we want to keep this constant. Keep this constant throughout the experiment. Vary this. So we are going to vary this. Change the gravitational pull downward and then observe this. Measure or observe this. Measure or observe. So keeping the total mass constant, if we vary the gravitational pull, we expect to see a variation also in acceleration. The more the net force, the more the acceleration. The less the net force, the less the acceleration. But we need to keep this constant. How do we do that in our experiment? That is the most important question. How do we do it? How do we keep the mass constant and observe this and see how this varies? How do we do that? Well, the experiment, as I showed you here, involves putting some mass here and some mass here. So we are going to say, okay, the first run, let's run the experiment the way it is. I'm going to pull this one down and watch this one accelerating. So both small m and capital M will be moving, will be accelerated. Now, if I have, if I borrow some mass from here, let's say I take some mass from here, small mass. Let's say initially I had 300 grams. Now I borrow 70 grams and put it right here. What I'm doing actually here, I am actually varying the Fg here, but I'm keeping the total mass that is being accelerated constant. I can run this experiment again. I borrow the mass from here, I put it here. Then what I'm doing is just essentially increasing the mass here, but then the total mass that's being accelerated, m plus capital M, still remains the same. That's how I do the experiment. Again, to make sure that the total mass that's being accelerated is constant, I'm going to borrow mass from the larger mass, take it to the, and then run the experiment. Take some mass from here to the hanger, run the experiment. In so doing, we're just shifting the masses. The total mass, small m plus capital M, remains the same. If I want to measure how much I'm pulling down here, that's the net force. I just have to multiply the mass on the hanger times g. If I want to measure acceleration, I need to figure out to put it here, another gate here. What do gates do? Gates actually are connected to a timer, and the timer tells me how much time a car takes to move from here to there, how much time the car takes to pass through the two photo gates. So timer here, and then I'm going to also measure the distance, this distance here using a ruler. What's the distance between the two gates? They are light gates. So by so doing, I'm trying to see if I can measure the acceleration. Remember, if I'm starting from rest, if I start right here from rest, then I can use that formula. I can use the distance is given by half acceleration times time squared, and therefore from here acceleration is twice distance divided by the time squared. So if I know the distance and the time, I can find the acceleration. So acceleration is just twice e divided by time squared. As long as I start the car close to the first gate. In other words, I want the initial velocity to be 0. So once I do that, I will have my data. I will have my data. My data will have, in general, I'll just make simple data here. So I will have net force, which is actually the mg, that's the net force, and then I'll have corresponding acceleration, which is twice d over time squared. Then I'll collect my data. I will have my data here. For different values of a net force, I have corresponding acceleration. I add the mass on the hanger, I have acceleration. I add the mass on the hanger, I have corresponding acceleration. I add the mass on the hanger, I have corresponding acceleration. So I have data, force of versus acceleration, and I might want to plot a graph to see if the graph tells me something. I might want to say, okay, let's put me acceleration here, meters per second, and then let me net force here. Okay. And then the kind of graph that I'm going to end up with will tell me something. So let's assume it's a straight line. A straight line. A straight line. So it will tell me that if the graph is straight line, it tells me that indeed net force is proportional or directly proportional to acceleration. And the slope of the graph line, which is the rise over run, will tell me the mass that I'm putting, the system mass. So let me mention that one here. So plot a graph of net force versus acceleration, or that is to say a graph of Fg versus acceleration. That graph will look like a straight line, and then the slope will tell us the what? The system mass. So slope will be equal to system mass. And what did I say system mass is? System mass is just capital M plus small m. So I can actually find the slope, and that slope will tell me that that's the total mass that I'm actually accelerating. If I find my mass this way, I can compare it by measuring using a beam balance. So you can now compare calculated slope with the calculated slope or mass with the mass obtained using beam balance. So you can actually measure using a beam balance also. So if we compare the two, then we can come up with percentage error as usual. We can calculate percentage error to see how far the theory deviates from the experiment, or to see if the theory works. Remember, why do we say here the slope is equal to system mass? Well, we know that, recall that Fg is equal to system mass, the total mass that's being accelerated, times acceleration. And if you isolate A, you end up with Fg divided by m plus n. So this is actually telling you that indeed the slope, which is rise over run, the slope tells you actually the the system mass. Okay, sorry. This is valid, but that's not what you want to say. Let's move down here. Okay. Why did I say the slope equal to the system mass? It's because Fg is small m plus capital M times small m. If I divide both sides by the system mass, I mean the acceleration, I'll end up with Fg over acceleration is equal to m plus capital M, which is equal to system mass. And Fg was on the y-axis and the acceleration on the x-axis. So if I divide Fg, that's the rise, divided by the run as acceleration, I get system mass. That's why I said the slope is actually equal to the system mass, according to Newton's second law. Okay, let's take a look at our lab. So the theory here takes you through the theory. You're going to have mass here. You're going to add some mass here just to have a mass that can be transferred easily to the small mass. Okay, and then let's look at the table. So here's the procedure. So when you are writing this, don't copy it. So do not copy it. Try to write in passive voice. Use passive voice. Like here, you say, effort was made to make sure that the air track was leveled. Or you can just say the air track was leveled. Then the mass of the car was measured. And then starting with no mass on the hanger, 40 grams was attached, like that. Do not talk about we or do not mention anyone. It should be passive voice. Number 4 says position the car near the first sensor. You say the car was positioned near the first sensor. That's passive voice. Okay. Here is the data already collected for you. The mass of the car is 308. You got to convert that to kilograms. So think about how to convert 308 grams to kilograms. So the actual system mass, that's the mass measured using a triple beam balance, is given here. Is the mass of the car plus mass of the hanger plus 40 grams. The 40 grams is just an added mass that will be added on the it'll be added on the car. So we'll have 40 grams here, and all of it will be about 300 something. What is that? 300 and yeah, that's 308. So 308, that's capital M, and 40 grams will be the mass just added on the car just to be able to transfer it, because we can't break the car and transfer it. So we are going to have 308 plus the 40 grams added on that car, and then plus the mass on the hanger, all of which will be the actual system mass. So if we use a triple beam balance, we find that the total is 353. Okay, so the mass of the hanger is about 5 grams, I think. So 5 grams plus 40 is 45. 45 plus 308, that's 353. Yep. So remember, mass of the hanger, this one is 5 grams. This is 40, 45. 45 plus 308, that's 553. So the total mass is 553 according to a beam balance. So back again here, the mass M here plus the mass that is sitting on the car plus the mass of the car is 353, just by beam balance. All right, so you start your experiment. You know the distance between the sensors is 50 centimeters. You have to convert that to meters, and here also convert to kilogram. So we are talking about this distance. Oh, it's not indicated here, but there is a gate here, another gate here. So the distance between the two gates from here to somewhere here is 50 centimeters. So that's not indicated, but note that's 50 centimeters. Then let's do the calculations. When there was no mass on the hanger itself accelerated everything. So the total mass on the hanger is 5. There was nothing on the hanger, plus the 5 together is 5 grams. 5 grams to be converted to kilograms, you divide by 1000. That would be 0.005. All right. Then you find the force of gravity, Fg. Fg, this is like Fg equal to mg. Then you're going to multiply the mass here, 0.005 times what? Times g, 98. Your answer will be here. and then your time is here. You are going to use the time to find acceleration. D has to be in meters. D has to be in meters. So convert this to meters and put D in meters here and time in seconds. Find your acceleration. The measured system mass, you just divide the force. The force you get here divided by the acceleration you get here gives you the measured system mass. Again, the force you get here divided by the acceleration you get here gives you the measured system mass, and put it here. The measured system mass can be compared with what you get right here to find the percentage difference. Go to the second row. Okay, we put mass 5 grams on the hanger now. The hanger has 5 grams, 5 plus 5 total. So 10 grams now is accelerating the system. This 5 is taken from the main car. So we borrow it from here. Take 5 from here, put here, make it 10, and let the experiment run. So we take 5 from the car and put it on the hanger, making the total mass on the hanger 10, and this will be 0.010 kilograms. The force here will be that mass you get here times 9.8. If you run the experiment, the time was found to be this, and the acceleration will be twice distance, same distance, 0.5. Well, I tell you. So find acceleration here and find the system mass. It will be F over acceleration. Your mass will be here. Percentage difference, that will be the formula here. I think there's a formula somewhere. Here, you can use this formula for percentage difference. You can use that one. Measure the value, actual value over actual value. That is the percentage difference. Remember, we found the measured value using a triple beam balance. It was 353. Convert it to kilograms. The actual value will be found here. It will be close to whatever you get here, then divided by the actual value times 100. Okay, so you do that. As you can see, we keep on adding mass on the hanger, and the total mass increases to 15. We add 5, 20, 5, 25. We add 5, 30. So the total mass on the hanger is 20 in this line. Then convert this into kilograms by dividing by 1000. You get the mass in kilograms here. To find the force that's pulling that mass, you multiply by 9.8. You get the force here. To get the acceleration, you multiply 2 times distance in meters divided by the time squared. This is the time squared here. And then you find the measured mass. Measured system mass will be the force you got here divided by the acceleration you get here. That will be the measured system mass. And then you find the percentage difference, again using this formula, whereby the measured value is 353. In kilograms, it will be 0.353. The actual value, the actual value will be the one you measure using a triple beam balance. 353 in kilograms is 353 grams in kilograms, 0.353. And then the measured value will be the one you get here, which is F over acceleration. All right, and then you just follow your syllabus to discuss the kind of errors you get here. What kind of errors you get? Are they too much? Are they too small? And what contributed to the percentage difference? What could have gone wrong? Think about the formula we are using. Think about the air track. We assume that it has no friction, but it doesn't take all the friction out. And we are also assuming that the car will be starting from rest, so we can use this formula. So if you don't start from rest, this formula might have some difficulties. There are problems with calculations. So there are so many things you have to think. Think about the procedure. Think about the assumptions we made, and that will help a lot to figure out the sources of error. All right, thank you so much. If you have a question, please email me.